The topic I'm going to talk about is the errors in time splitting for numerical integration of semilinear ordinary differential equations. At the beginning itself, I will confess that I'm not a mathematician. Uh, I'm basically a mechanical engineer who moved into atmospheric science and, I mean, do a bit of modeling for atmosphere. So I did find a few problems which was kind of which I discussed with Vasu, and interesting things came out of it. So I would say that largely my role, you could say, in some sense, was asking awkward questions, and it was Vasu's way of kind of to answer these questions. So I mean, I hope if there are any mistakes in my presentation, then it's just mine and not certainly not Vasu's. So this is the outline of my talk. I'll begin with a brief background. As I said, this is a study with the result of discussions with Vasu. And actually, let me confess, this is about slightly old, the work that I'm talking of, but as of now, it is still relevant. The same questions which happened about maybe a decade or two before, again, are kind of, they are still relevant today. I'll show that in a moment when it comes, especially for atmosphere or climate modeling. And when we look at numerical methods in atmospheric general circulation model, AGCM as we found that changing a numerical scheme gave very different results. And that even today we find that when we use different numerical schemes, we get different results. And one of the major things when we were looking around was that we found that simulations were very sensitive to prescription of cloud parameterization. Now, cloud parameterization basically is a nonlinear function, and it is kind of doesn't happen all the time at every time step. It is only based on different conditions. For example, the stability of the atmosphere and existence of large scale, low level flow, that is in some sense convergence, that you can get clouds, and you have to parameterize. The problem in cloud parameterization is that individual clouds that we are looking at, their size is about 1 kilometer. And the typical grid scale that we look at in our models is about maybe 10 kilometers. Of course, these days we are doing weather forecasting models which are as fine as 1 kilometer. But most of the time when we use models, the global models, we use it in the order of about 100 to 10 kilometers. If you are looking at climate, that is long-term system, which you have to integrate for a very long time, then you use something more like 100 kilometer. And when you're looking at shorter time scales like seasonal forecast or something, then it's in the order of 10 kilometers. And what I would like to highlight, I'll show that in a moment, is that even today with different models of ocean atmospheric GCM, that is OAGCM, we get different results. And when we use only the atmospheric counterpart of the OAGCM, we also get very different results. And there is no easy way to pinpoint the cause in a complex system. And when we are looking at different numerical techniques, such as semi-Lagrangian methods, which are difficult, I mean, it's kind of, I wouldn't call it arbitrary, but you do a lot of approximations there, and it is difficult to quantify the errors or determine the right method of splitting various terms in the equations. So this was the kind of background that we started asking, or rather I was asking the awkward questions to Vasu, and patiently he tried to explain to me, and through that we came to the present work that I'm going to discuss. The first thing is I would like to talk about the effect of numerical techniques and general circulation model simulations. This was some time back again, but it is still as relevant today as when we made it. It was about maybe 15 years back. We conducted studies with an atmospheric GCM, and we used two methods, semi-Lagrangian and spectral methods, to study the monsoon. And in these models, only moisture advection was done differently. That is, the entire rest of the model was all done using spectral techniques, but the moisture advection was done using a semi-Lagrangian. The reason is that the undershoots or the Gibbs oscillation that you find in models can kind of create negative moisture, which is unrealistic. And there are no easy ways to kind of handle this problem. So people have kind of shifted to semi-Lagrangian models for moisture advection. Of course, today most models are completely semi-Lagrangian problems. But when we did this, only the moisture advection was done with the semi-Lagrangian method. The rest of the model was identical. The top one is the semi-Lagrangian results for the June, July, August mean picture of rainfall from the semi-Lagrangian method. The same result is from the spectral methods. And you can see that when we look at rainfall over different regions, and this is the Indian region, which is not very clear from here, well, we got very different results over, especially if you're looking at the monsoon, but even at other places. For example, the Central Pacific region, where you this kind of happens to where you have a lot of El Nino and La Nina happening. There also the results were very different. And the bottom picture is what we call as a climatological picture, that is from observations, the kind of patterns that we get. And both gave very different patterns, and you could say in some sense both are very different from the observations. So this kind of started a discussion with Vasu about what is it that causes it. And we thought it was the way the models are also split. And we further looked into it. And one of the problems, as I just told you, was about the parameterizations, which also, so when we looked at the intercomparison, this is a recent work that is as part of the climate change project, the IPCC, International Panel for Climate Change, which I think is is in news because of the climate change problem, and all the results from the climate change which are being used is from these AOGCMs and AGCMs. And as part of this, they are compared for historical scenarios. There are various scenarios they do. For example, they do a scenario which goes from the present day to 2100 or 2200 to see how, when the carbon dioxide is changed or any greenhouse gases concentrations are changed, what is the kind of climate that's going to change. But what we essentially look at here is what we call as historical scenarios. That is, we start from 1850 when pollution kind of became less, and today when it is much larger. For example, if we look at it, then it must have been around today it's around 420 ppm. At that time it would have been 280 or either 380 or even less parts per million of carbon dioxide. And when we compare these models, we find that there are significant differences when the models, the forcing is the same between, that is basically the only forcing that we are giving is changes in greenhouse concentrations, but the results we get, which, sorry, this is a different one. But first, let me talk of the cumulus parameterization, which also has a major impact, and most of the models give identical results when you kind of switch off the cloud parameterizations. And as I said, the clouds occur at a grid scale of about 1 kilometer, and most models have a resolution of about 10 kilometers. And while this cumulus is very important, it is a major forcing function as a heat and moisture source. And it depends on the empirical formulation of the clouds. That is, we take some observations and say that, okay, this is how you are going to get your source, the moisture or the heating source. And looking at various field experiments, different assumptions are being made about how the clouds are formed, and within the model, how we kind of do it. Because the model will have data only at 10 kilometer resolution, and we have to kind of put this effect at 1 kilometer resolution. So there are various ways of doing it, and different schemes give different results. And if we look at what we call as a dry model, where we switch off all the moisture processes, then almost all the models give the same results. And the problem with the cumulus scale forcing is episodic. They don't occur at every time step, but occur at every grid point. And they don't occur at every grid point at the say every time step. Whenever the conditions are kind of favorable for the rainfall to occur, or when there is a huge instability, the moist static instability of the atmosphere, if it is large, and the large scale causes this instability to occur, then clouds form, and the instability is kind of removed, and the atmosphere again goes to near stable situation. And we also notice that there are differences between AOGCMs and their AGCMs. Of course, In AGCMs, we allow the conditions for ocean to evolve, while AGCMs we just prescribe it externally. So this is with cumulus forcing, two different methods. One in which we look at where you kind of use a model which the top one is of course observation. The middle one is where we are using what's called as a scheme, where the large scale uh, stability of the atmosphere plays a major role. The bottom one is where we call as a moist convective adjustment, where the rainfall occurs if the entire grid becomes unstable, and that occurs in the vertical direction. And if you look at the difference, you find that both of them are giving significant differences, and the most major difference is again over the Indian region. And you also find some differences over the Pacific region, that is the equatorial Pacific region. And even today, this is a major problem for most present day models, and it is kind of related to the fact that is the cumulus parameterization, which is a episodic forcing function, and the way you do it. And even today, there is much research going on it, and there is a new way of thinking of using large data. That's because we have satellites giving you a huge amount of data, and people are trying to look at AI and ML techniques to do this prescription, because it's a largely empirical method that is being used. So that's also a new area of research which is still under, which would say is just under progress. This is the Indian monsoon simulations in IPCC. I know it's a busy slide, but what I want to show is that at the top you have all the observationals. Even between observations, you get slight differences. This is from IMD data set, and that doesn't show any rainfall over oceans because they have only based on the station data set. That is actual observations. Then these are like where the station observations and satellite data is merged. And this is another merged product. So that's why you get rainfall details over both land and ocean. And it is reasonably able to capture the major regions of high rainfall. One is over the northern Bay of Bengal, if you could see, and the other one is over the Western Ghats, which here may not be very visible, but you can see it in the G2CP rainfall data set. And these are various models that we are in which were used in IPCC comparison. And there are a huge number of them, about I think 20 models took part in these historical simulations. There was also, for the first time, India took part in that from IIT, and the Indian Institute of Tropical Meteorology participated with its own Earth system model. I guess this result is from one of my former students, Rajendran, and that has not been included in it. But we know that that also participated, and it gave reasonably good monsoon results. So what I would like to point out is that there are significant differences between different models when it comes to kind of simulating the monsoon, let alone predicting it. Even for simulating the monsoon, there are results, and most of them do have a problem when it comes to having rainfall over the core monsoon region. That's what we call it. This region is called as the core monsoon region or the Indo-Gangetic region running parallel to the Himalayas. And that most models have a problem. They underestimate the rainfall. So that's been a problem which we looked at even 15 years back. And even today, we find that the problem exists. And even if you do with AGCM simulations, this is with AGCM models on the right, and with the atmosphere ocean GCMs, the rainfall becomes slightly better, but the rainfall over land is still not kind of is missing in most models. This is across models that we are looking at. Most of them, if you compare their own model, the atmospheric GCM and the atmosphere ocean GCM, you find that the rainfall over the region is higher in atmospheric GCMs as compared to ocean atmospheric GCMs. And quite often you again find that the rainfall is kind of less over the Indo-Gangetic plain. To the north, most of them are capturing the high rainfall over the Himalayan region, the foothills or the what we call as orographic rainfall, but when it comes to the actual rainfall, there is still a problem. And so it's even though we started looking at some of these aspects 20 years back, there the questions that we asked at that time are still relevant, and that kind of led to a discussions with Vasu, and we thought we'd look at a very simple model, a semilinear ODE or a PDEs converted into ODEs, and that was like the background on which we started this work. And how we split the numerical schemes was important, because in models we have a multiple scales which may be involved. For example, in atmosphere we have very fast scales such as the gravity waves, which run almost at the speed of sound, and slower waves which run as which we call as Rossby waves, which have a wave speed of about only 10 meters per second. And since we have to do very long-term integrations, one of the things that also we were discussing was whether we can improve the efficiency of time integration. And what we found was that when we do the convective heating, that is the cumulus heating, if we at what time step we do, which is an episodic heating, which I'll talk about it later, then how the way we kind of prescribe it on within the time step, how when we do it, it could be the results could be sensitive to that. And splitting of numerical schemes invariably involves errors. The way we split it, we will all know that it gives you errors. And sometimes the errors could lead to even numerical instabilities. So what our idea was to look at a generalized framework for ordinary differential equations, which could be used to analyze errors due to semi-discretization of evolutionary PDEs. That is, we assumed that there was a spatial scheme, and in time we were looking at different methods of discretization. So this is the framework which we started looking at. So it is basically an ODE, a very simple one. That is A psi plus B of, which is a function of psi. A is a linear part of the model, which basically comes from discretization. And if you look at in this case, it's A is a n by n matrix, and B is a nonlinear function. And psi of t and psi 0 are the n vectors. The psi at time t and psi 0 are initial condition. So if we look at a forcing function, we get this can be split. That is, the nonlinear part could be split into what we call as R of psi and P of psi. R is a nonlinear function, and P represents a parameterization, such as cumulus heating, which we have been discussing. It's a nonlinear forcing which is applied to the system, and in climate models is a major source of uncertainty, and it's even difficult to estimate the magnitude of error which happens in cumulus models. And such a system could be error could be due to discretizing an evolutionary PD in space, and with time variables. A typical example is the advection diffusion equation, which could be of this form, which I think all of you are familiar. So basically a diffusion where u is a nonlinear function and d are constants. And when we put f of u as u, then we get the Burgers equation, which is already familiar with most of the people here. So we looked at the framework, and we thought we will discretize this equation approximately over a domain with grid spacing of h, which is 1 by n plus 1. And we approximate the function as u of kh of t, and so on. With these approximations, we get a system of ODEs to approximate the PDs. And let's say for convenience, we use a central differencing, and this is what we get. And in terms of the framework, we can write it as xi, which is the vector of n vector, and a tridiagonal because of discretization, and b of xi, which could be a function of u at different times. So if we use other techniques, this same discretized framework would still be used even if we used finite elements or finite volumes. Of course, you would have different A's and B's, but the same technique or the same framework would still be used to analyze errors in these methods also. So now we look at different kinds of splitting. We define two types of splitting. The first is to split the ODE in the previous equation into a system of ODEs, but we don't do any approximation here. This we call as the continuous splitting. The second kind is where we discretize the time splitting. So we will now propose to determine if either continuous or discrete splitting causes error. That is whether if you are doing a continuous splitting as we just discussed above, or it is a discrete splitting, would there be errors even when we do a continuous splitting? So that's what we are going to look at next. So when we look at continuous time splitting, we thought we'll first simplify so that we can have kind of a grip on the problem. And for simplicity, we consider a case where both A and B are linear. And for the previous equation that we discussed, it's also B becomes a matrix, n by n matrix, and the solution will look of this form. That is xi of t is equal to e raised to p a plus p plus xi c. So if we look at the continuous splitting, it can be written as in two stages. First is the stage where you kind of solve for xi star. We're using only a with the initial condition of xi 0. Then in the initial stage, next stage, we compute the xi double stars, and which is uses only the function of b, where the condition is xi double star is equal to xi star of. With these two time variable solutions, we combine them at tau equal to t, we get xi star is equal to in this form. So now we would like to look at the error between the analytical and the approximate solution. And we find that it is related to both the matrices A and B when we are kind of looking at the error between the two of them, between the analytical solution and the approximate solution that we are getting. We find that the error is 0 only if A and B commute. That is, AB is equal to B. Otherwise, we will only get an approximation, though it will be a continuous one. Thus, we can say that in general, continuous splitting introduces error, but this is essentially due to the commutativeness of the matrix. So next, we thought we will look at the discrete splitting. We still consider the case where B is linear. The analytical solution that we had seen is of this form, which I'm reproducing here for convenience. And we consider the discrete time marching scheme, such as first order explicit Euler, which could be written in this form. And there are various ways in which you can approximate E. And we write xi t as an approximation of xi at time step t. You could do by R, which is a kind of an expansion of E, or an approximation of E with Rz. And there are various ways of doing this approximation. R of z could be equal to 1 upon 1 plus z. Another way could be that R of z is equal to 1 by z, which gives you the Euler implicit scheme. Or in this case, you get, when you use R of z is equal to 1 plus z, we get the explicit scheme. Or if we use the approximation R of z in this form, we get the Crank-Nicolson. In short, the kind of approximation we make for the exponential determines the numerical model. So based on the exponential approximation, we can write it in the following form of A and B, even though right now, please remember that A and B are linear. And we now determine the error with this system. We need to find the error between RH of BR and R of H of A plus B. Based on various approximations to E, we can estimate the errors. For R of Z is equal to 1 plus Z, the error would be of this form. While R of Z, if I do that, I get the errors to be of this form. Now, if you notice, previously when we did continuous splitting, we got basically the errors due to commutativeness. But if we examine the errors here in these cases, that there is no kind of a pattern that we see here, that the commutativeness doesn't really play a very major role in this case. And so if we can say that in discrete splitting it would exist even if the matrix is commuted. So that's the major thing that we found. So next we started looking at semilinear systems. That is, up to now we have been looking at purely linear systems, and we have considered B to be linear. Now we consider B to be nonlinear. So d xi by dt is equal to A of xi plus B, a function of xi. Now this equation would satisfy the nonlinear integral equation of this form, where you integrate between 0 to t. Now, what we need to do is to approximate the above integral. We consider the solution at t plus h with the initial condition at t, and we can write it in this form. We use the trapezoidal formula for this purpose, and we get the xi of t plus h in this form. And we can now approximate the exponential using different formulae, that is with different e's ways we can use the formulae, and from this obtain the time marching schemes. We prefer to concentrate on 3 time level schemes. That's because most of the present day schemes, regardless of the kind of numerical, the spatial discretization, whether they do spectral discretization or they do finite volume or pure semi-Lagrangian grid finite difference methods, they all use 3 time level schemes, that is in time. So when we look at spectral schemes, most of the time they use a 3 time level leapfrog scheme, while the other ones, mostly finite volume or finite difference today, they use the 3 level semi-Lagrangian scheme, which is also so. That's why we thought we will concentrate only on the 3 level schemes. So even we thought, so there are times when we use a 2 time level scheme, but then we kind of use a dummy scheme between t minus h and t plus t h and t plus h, and put a t plus h by 2 as a dummy time step. So in effect, it becomes again a 3 time level scheme. So we continued with the analysis of the 3 time level schemes, and we consider the same equation, that is equation 17, and we try to integrate it between 0 to t, and we integrate this within the interval t minus t to t plus h. And we have used the midpoint quadrature. You could use any rule here, and which we could write it in the following way, and it can also be written in this method. So we now need to approximate the exponentials as before and obtain different time marching schemes. One of these would be when you approximate it in the sense of r of 1 plus h, then r xi of t plus h becomes in this way. Another scheme would be of this particular form. And if we look at these equations, this particular equation could be split into 2. And the first step would be this calculation, and the second step would be this calculation. If we use the second order accurate scheme using the approximation of r of z is 1 upon z minus inverse, we get the time marching scheme of the following form. So if we look at these two equations, we find that the splitting of the schemes in these equations 25, 26, and 27 and 28 are not identical. So obviously there will be different errors between these two. Another problem that we found, or rather Vasu identified, was that in splitting the term RH to R2HA into RHA squared, as in equation 24, which is this equation, we need to write the exponentials with the same argument, otherwise there will be errors because of this. So, and hence there we could split it in this form, another way, and which leads us to the scheme of this particular way. And it's interesting to note that when we look at xi star and xi stars and xi, they are independent, and hence the scheme is amenable for parallel computing. That is, you can do the computations in parallel. For such this equation, it might look small, but if you're looking at an atmospheric model, doing it independently certainly kind of hastens up the uh, simulation. So we came up with a new proposal for splitting with the same exponential, that is using HA, 2HA instead of HA squared. Now we avoid errors due to exponential, and we get this kind of a equation. And now we make a linear approximation between t minus h and t plus h. That is xi of t and t with the where m now is the slope, approximate slope of b of xi at any time step s between t and t plus h, where we approximate the slope in this way. And we know that b bar approximates only at t and doesn't approximate at t plus h and t minus h. So now we replace b by b bar and we integrate to obtain this particular equation. Now if we look at it, we notice that all the terms have the same exponential, 2ha. Using the approximation for exponentials, we will get the semi-implicit scheme of this form. And once we get this, it can be used for splitting. So this is the new proposal that we did, that this splitting would prevent errors in approximation of the exponential. Another alternative would be based on the same framework would be of this form. In both these splittings, the first term is explicit, while the second term is implicit. So but if we eliminate xi star, we get back the original scheme, and so it's identical to the original scheme. But if this kind of a splitting which gives you the original scheme is recovered may not happen if we split it in some other form. So again we consider the same semilinear equation ASI, and we now consider the splitting of a nonlinear term of again with this form. And sorry, there seems to be mess up here, but again we kind of look back and see that a or b of xi, as we said, is a function of r of xi, which is a nonlinear forcing, and p of xi, which is a cloud scale forcing. That is, we are splitting the nonlinear part into this form, and we need to parameterize the models as we have just discussed, as the cloud cannot be resolved in most atmospheric models. As we said, the clouds are a major source of uncertainty. As shown previously, the simulations are very sensitive to the prescription of cumulus parameterization. So as discussed previously, they occur at scales which is smaller than the grid scale of the model. There was a previous work of Kaya which showed that the time truncation in the splitting was unacceptably large due to the parameterization related heat source P that we had looked at. They showed that only very small time steps, which are of the order of 60 seconds, they get results which were similar to the unsplit teams. So we wanted to ask whether these errors are due to when we even look at a steady state. So we examined the steady state solution, and we looked at whether it is the improper splitting which can cause these errors. So we looked at the scalar ODE of this form, df by dt plus beta f is equal to g. We assume beta to be greater than 0, and they are both beta and g are constants. This gives us the steady state, f is equal to g by beta. However, we use an improperly split scheme, as that was used by Kaya. We get of this form, we get a splitting which gives us, even in steady state, this kind of an error. In terms of framework, this is what our would show when we look at this, and leads to this error. Comparing with the equations for proper splitting, we get which is in this form. We note that the proper splitting of this should be of this form and should not be 2 HP of xi. So when we look at this proper splitting, and what it means is that we need to calculate P at xi of t instead of xi star. And then again, the right kind of this one steady state solution is obtained. And using xi star instead of xi t instead of xi star does not require any additional storage in three-level schemes. So it is as good as the original schemes. And of course, the errors could be eliminated. Next, we look at one nonlinear equations. And we looked at a nonlinear equation which could be split in this form. It's basically depends, shows the population dynamics of bacterial colonies, which is of this particular one. UXT represents the population density, example of a bacterial colony at x of t. A, it is its growth rate, and the mutually competition annihilation coefficient of b of x of t. V is the advective velocity, and d is the diffusion. If we consider the case where d is equal to 0, that is, there is no diffusivity, a and b as constants. Based on this, we get uh, analytical solution. And under different conditions, if here a and b are constants, but if we get a and b are constants and b is a function of f, then we get the following solution. There are various solutions that we get, and we use this as a test bed to see how different schemes behave with this. So these are the results. I'll quickly go through it for lack of time. And these are the two metrics that we used. One was, of course, the correlation coefficient between the analytical solution and the simulated solution. So the first test case was where we looked at an initial distribution of this form. And we used a domain of 15 to 15 and plotted graphs in terms of A by B. And we used 400 grid points. The values of the parameters were of this form. And this was the initial condition that we got. And we looked at the upwind method at time level 4. And this is what happens with the leapfrog scheme. That is, if you look at closely, the cross points are the simulated, and plus points are the analytical solution, which clearly shows that this upwind scheme is doing a good job. While leapfrog scheme, there is a difference in phase between the two of them. So in short, if you look at the unsplit scheme, these are the various errors that we are getting. The correlation coefficient kind of reduces, especially for the leapfrog scheme. It's pretty bad. And but interestingly, this is the most commonly used scheme in most atmospheric models. I'll skip the rest, but this is for the split schemes, various schemes that we had looked at. And again, we see that the leapfrog scheme doesn't give a very good splitting. So this was a different test case. I'll skip for want of time. And this is the various unsplit schemes, the errors and cross correlation coefficients, and the analytical area, the areas under the curve, and the differences between them. We find that some of them are good, some of them are not so good, and the cross correlation is much better, but except for the leapfrog scheme where it is about 0.72. So this is the various schemes. I will kind of, I'll now talk only of the test case 4, which was periodic and had 400 grid points. And we used, again, with initial distribution of this form, and the upwind method in this form gave you these results. There was a kind of a singularity which was captured, which is not there in analytical solution, but this is what we got after a time level 1. This is a time level 4, and this is the Euler split scheme. And the semi-implicit scheme that we did gave you this, while the Euler split solution of Kaya, similar to that, gave you this solution, while this, of course, there was a bit of a problem with this condition, but it gives you a area which is closer by R splitting scheme as compared to the previous one given by Kaya. So what it means is basically the errors should be, I mean, it should be properly split, and the errors are kind of reduced even in the numerical scheme. If we actually do it in real GCM, there is no easy way to understand it. That's why we looked at a very toy model where the same schemes are used, but in a very simpler equations. So this is for the test case 4, and I will now, the problem with incorrect splitting, which I was talking about, that is, if it is not split, and error gives you, these are the errors that we got. I will skip that, and so these are the solutions that we got with the split solution at 4, and this is with the semi-implicit solution, that is our solutions. As I said before, they are, it's better with this rather than with the previous one. So this is the summary, and I'll not read the entire thing for want of time. But basically, the thing was that if we don't split correctly, then we get errors even with continuous splitting. Or even if we use discrete splitting, if we don't do it in the right way, then we could get errors which could kind of get multiplied in nonlinear models such as the atmospheric GCMs or the atmospheric ocean GCMs. So these are the other summaries. I will not talk about it. Finally, I would like to acknowledge my former student Srivatsa Brahma, who conducted all these simulations as part of his MS thesis. Thank you. I'll take any questions if there are.